So here we go. You test your model. Okay. What you need to know is that there is a stability condition. The time step is constrained. Okay? And it's called the Courant-Friedrichs-Levy condition, or in short, CFL condition. And what it means is that the time step, let's activate the mouse, the time step has to be less or equal the grid spacing divided by G times H, the maximum value of the total water depth. What this implies is that you have a surface gravity wave that it within one time step doesn't propagate further than one grid space. So this is what this condition implies. If you don't satisfy this condition, your model will crash, will not work. Okay, and in a more complex three-dimensional hydrodynamic models, this condition is often the toughest condition, because if you are working on deep ocean applications, you have to work with terribly small time steps. You need many iterations, and this will prolong the simulation time significantly. So this is the so-called CFL stability criterion for these surface waves. So now we want to test it, and the way to test that is to have a channel, one-dimensional channel, you've seen here, okay, and in the middle, I just have a elevated sea level initially, okay. You can imagine that you have some walls that you remove, and it's a 1 meter elevated sea level, and then it will propagate in two directions, okay, as shown here by these arrows, and the channel also has closed ends. Okay, so what you expect is actually some sort of reflection at the boundary. Okay, 1,000 meters long, 10-meter deep, horizontal resolution is 10 meters. So, and that's how you test. Why you do that is it's because it's a symmetry test. What you want to do is that on the right-hand side of the channel, exactly the same as a mirror image should happen compared to the left-hand side of the. Okay, and what I want to show you is only one part, only the right part of the channel I show you. And let's have a look at it. Here's the simulation. Yep. 3 panels. Okay, when we do that a couple of times, but just before I repeat the simulation, I want to show you what's shown. Okay, so the top image shows you the structure of the sea level. Sea level elevation can be positive or negative. Okay, and you can see it starts at 500, so it's in the middle of this channel, and 1,000 is the right boundary. Okay. The second panel shows you the horizontal velocity in meters per second. This is the depth-independent horizontal flow in this shallow water model. It can be positive or negative. In addition to that, I'll also show you a velocity stick plot, but this sort of doesn't really work out here or so, but just showing you that you can also use something like trying to actually show arrows of the movement, but it didn't really work. You can ignore. No Shapiro filter in this example. Okay, I demonstrate you the Shapiro filter on the next slide. Just have a look at it again. Going back, now start. You can see the wave. There's a wave propagating to the east, being reflected, and then essentially what happens after time, it actually meets the other part of the wave, which is reflected on the left side of the body. Okay, and if you check it out, it's actually the phase speed of these waves is square root g times h. It has nothing to do with the with the velocity that you have. The velocity is the instant flow that is created under such a wave. Okay, so this is one example. And if you check both sides, you see it's symmetric. You also see that there is a little bit, there is a sort of the wave has almost two parts. It's sort of breaking apart into two bits. Is that a real feature or is that a fake feature? So we actually know that this happens that this can happen. But if you apply the Shapiro filter, you get a much neater solution, but it gets rid of this feature that might be significant. So let's see how Shapiro filter looks. Look at this. Shapiro filter looks very nice and smooth. Shapiro filter where you set the parameter to 0.05, this epsilon. But eventually you might actually filter away a true part of the physical solution. Okay? Why can this happen? That this separation into two is something that we call amplitude dispersion, which means, and you learned that actually, if the wave propagates at a phase speed of square root g times h, the propagation will be actually intensified in regions where the wave is thicker, in regions where the water depth is increased. Okay, and due to that mechanism, one single wave might actually separate into two or more single waves. Okay, so this is the first example of long waves in a channel. What you can also do with this model is you could actually place a wave pedal somewhere, a wave pedal that just lifts and lowers the sea level. Okay, all right. So that's one example.